All right, welcome to a coach's workshop session for the 2024 Science Olympiad Optics event. This is an event for both C and B divisions. This is an event that hasn't been presented for a few years, so you may not have much experience with it. I wanted to highlight a couple things. First off here, turn on a projector, and that this is one of these combination events. In this case, though, you're not actually building a device. The students are performing with an apparatus at the site itself during the tournament, but they're also taking a written exam with questions based on the topics, and a broad range of general topics in optics itself. So while my projector warms up behind me here, as is true in both of these events, there's sort of a 50-50 split in terms of the points awarded for the performance, both on the written test versus the actual device performance, or in this case, again, their performance with an apparatus with laser beams and mirrors. So I wanted to demonstrate that to you for this event right here. Erase my optics title off the board. You can see behind me here, I'll try to brighten it up for us a little bit. Zoom in a little bit as well. Here is the breakdown again of the point totals. That there'll be an exam worth 50 points. You're using mirrors, or the teams are using mirrors to redirect a laser beam to a target point. So the number of mirrors used can earn up to 20 points. That's 4 points per mirror for a maximum of 5 mirrors. But the laser must strike the mirror in order to receive those points. Then there's an accuracy score of 25 points based on how close the reflections off the mirrors put the beam on a target point affixed to the inside of the device. And then there's an extra sort of a bonus for the C division for both teams, and that there is a barrier with a mirror placed on it. If the beam actually intersects that mirror as part of their setup, they can earn an extra 5 points. For the C division, there are 3 such barriers, any one of which may possess that beam. So it really quite complicates things as well. So what I want to do is actually have a device setup here. I'm going to switch over to that device setup and show you what's going on, because experience in the past has shown us that, again, for the exam portion, it's more how the individual teams study and prepare, bring some materials perhaps to help them work out as resources. But the exams, learning about the topics and concepts, maybe even doing a little bit of mathematical calculations or reflection angle or so forth, or things that the students can pick up on their own, or you can help direct them with that. But half of the score here goes entirely towards how they can achieve placing the mirrors to redirect the laser beam. And that is extremely challenging task already for the high school students. It's unbelievably challenging for the middle school students. So I'm going to go over and show you that actual setup here, see just how difficult that can be. I'm going to change our display here to zoom in on that for you. And there it is. I'm going to step over to that actual place itself and let you actually see just what it is again that they're tasked with doing. There are descriptions and examples of setups, and you can find again online probably some short videos of this. But let me show you some various options that show up here. What I'm going to do here first is I'm going to turn on our laser. It's just a simple laser pointer. And you can see on here as it goes through that the laser pointer is entering here, is striking this mirror here. You can actually see the laser dot there on the video, striking this mirror here, striking this mirror over here, and then reaching a target point over here. And that target point is barely glowing in the video there on this back wall. Here is the barrier. So if I was to remove all the mirrors, which I'll do in a moment, but not yet, the idea is the only aid that the students will have, and it's faintly drawn on here, so not showing up on the video, is there is a line drawn on the tabletop or on the sheets of paper I have here. It's a straight line from the laser to the target point over here on the wall. So that's one simple straight beam that shows up. But when the students are asked to position the mirrors, the laser beam will not be on. All they will have is that pencil line as a point of reference, and that is extremely challenging then to gauge from. Because let me show you this while things are set up here. You can see this one simple mirror right here. You can see the beam point over here on the wall. I'm going to barely rotate this mirror and watch what happens to our beam position over there for just a very, very slight rotation. I didn't rotate it much at all there, and you can see now that the beam over here is totally off this far wall. It's missing down here somewhere in the corner. And so that shift in position right there, as I'll move it back now, is at the most an extremely tiny shift, because what the students will not realize, both the middle school and high school students, is how critical the positioning is to extremely tight tolerances and angles. So let me step back over a minute to the board, describe what I'm talking about here. Find my camera control. Here we go. Looking back over here at the board now, referring to the fact that this is our mirror surface here. All that's involved with these mirrors, they are flat mirrors, is the simple law of reflection. It means the incident angle equals the exiting angle. So if this was like a normal to the mirror surface, it's quite simple that the angle of the laser beam striking that surface is going to be equal to the angle that it leaves. This is a fairly simple geometrical problem of straight angles, and the fact that however they align those mirrors in the little test box over there, they can count for the angle of incidence equal to angle of reflection if they know what the exact normal line is here. Hence the importance perhaps of using templates. And I'll demonstrate that, talk about that in a moment. But what they often don't realize is if you've got a beam that comes off like this, make a straight line for us there. That while the angle change will be small, if I tilt this right here, just a simple 1 degree angle, I tilt this by 1 degree, hence I'm altering this beam path here, that what happens is, as we roll these guys up bigger up here, is if you're down very close to the mirror, then the displacement of the beam here in linear distance is very small. And this does scale literally with distance. So say this right here was just say 1 millimeter. Got it blown up here to try to 1 millimeter. Well, on your ruler scale here, that's not much at all, and you're not much off the target over there. But if I go off a much greater distance up here, it scales literally. So if I get, say, 5 times farther away, so my distance from where the laser beam strikes the mirror to where it's striking a target is 5 times farther away in here, and all of a sudden, this scales again literally. This becomes now a 5 millimeter error that shows up. And so, hence, if you go back and look at the box here for a moment, what that translates to, looking back over at our box, if I was to have this central mirror right here off by just a fraction of a degree, right, that's going to increase the way it's off striking this mirror. There's a finite distance there. There's an even longer distance going over to the mirror over here, so that displacement increases and increases. And it has to reflect again to hit our target point over here, so it increases again. So the point being is, in the last years when this was run, all the teams did very poorly. Both of the teams did not even successfully get the laser beam to even hit anywhere on the target side of this box, because these tiny little adjustments, and they were not measuring things precisely enough and keeping things precisely positioned in the box itself. And I've got a fairly complicated setup here with 1, 2, 3 mirrors going over here. So even if you carefully position 2 of these 3 mirrors, and one of them again is just slightly off from position, talking about a tiny, tiny angle here, you can easily throw the beam entirely off. But what does that mean for your students and when they're performing is you do not have to build such a box. You do want to give them several mirrors to practice with. In this particular case here, doing this more as a demonstration, but we can use these mirrors at our own regional site to test. These are just some really inexpensive compact mirrors. We've broken the mirror off the other side of the compact and glued them to these little wooden bases to be in place here. And so you can get some mirrors quite simply, but they absolutely must practice this kind of a setup and alignment with an actual laser beam. Again, you don't need this entire box set up. Laser pointers, everyone has lots of laser pointers. I'm having a green one here because the green laser pointers are bright enough to see in a well-lit room, but you can use this as standard red laser pointers as well. Some way to mount that so that it's fixed, and some way such that you have then a fixed line. So I'm going to go ahead and move this off here. I did not have my fixed line drawn in place here, but I'll use the ruler to indicate that. I'm going to go ahead and actually draw a line down here just to show you. And this will all be set up again by us at the actual regional competition. There will be a sharp pencil line, and that is their reference. And the mirrors, by the way, will be covered in some sense. I have these little paper covers that we cover our mirrors so that while we are watching the students, there's no way that the laser beam got inadvertently turned on, which would not be in our case. We'd be sure our mechanisms are totally off place. That all they have to start with is a bunch of mirrors. I can position this wooden block anywhere. The rules do not say where it is. It will be the same for all teams. This wooden block might be positioned anywhere along this line. Add to the complexity again, for the high school division, we'll have other blocks to put out in the beam, and they can be randomly placed to the side like this, or one could be forward, one could be back. They could be anywhere. And you expect more complexity as you get to higher levels. I can sort of guarantee at the regionals, they will be very simply placed because, well, again, we're just dealing with straight lines and angles, a simple process of reflection. The critical need here is those angles must be extremely precisely measured and determined. So students can bring all sorts of tools, all sorts of templates, anything they want, and I would strongly encourage you to have them figure out what works best for them. A tool can be a protractor. Definitely need something that can measure angles here. And then again, the mirrors will not be positioned. We'll have them set someplace else off to the side, outside the box, so they're not being bothered there. And the teams can choose the number of mirrors that they want. At a minimum, you're going to need two, because there's no way a single mirror can get the laser beam around this block to hit our target point over here. So they'll need to deal with at least two mirrors, and then they'll have to figure out with their protractor, or I would suggest again, creating a version of the protractor. And let me show you what I suggest to do to increase their accuracy somewhat. You have the dimensions of this box, so you don't want to use tools or templates that don't fit easily inside this box here. But with the protractor, as you can see from a distance there, the angles are small and it's hard to measure. So here's a good suggestion. Go back over to our projector display here. You can create this by various ways if you have access to a nice big printer or some other aspect of that. Place this over here. But if I place this on our document camera, or you can, since it's a clear protractor, you can place it on an overhead projector, but most everybody has the newer technologies now. If I place this on the document camera here, you can already see how much bigger are the divisions between the lines to mark the degrees, how much more resolution I have, in other words, in seeing tiny angles. So this is obviously too big. This is not going to fit in our little box over there. But definitely, if you do not want to bring, I've seen students bring these little bitty pocket protractors in to try to measure these angles. That pocket protractor is just so unbelievably tiny that you can't precisely measure those angles at all. So I would suggest something like this. Build yourself a nice big template here. I can zoom out from this. That's as far as I can go here, so I'm a little bit too close in with the projection system here. But do something of that nature, where you can then sketch or photocopy or take a picture of it or so forth, or just do this with your normal thing. Make it up bigger so that instead of a protractor, that's the real physical size here, imagine, I'll sketch this off just crudely and quickly on here. Didn't have time to prepare a whole big one, but imagine if you had not this small protractor. Imagine if you had a much bigger protractor, say of this paper size here. That would allow you then again, versus the really small protractor here, to measure those angles a little bit more precisely and more specific in there. So what the students are going to have to do, and they have to do this within 4 minutes. So it's an incredibly short amount of time, is to come up to this box. They will not know where this block has been placed. They'll see that for the first time as they come up to it. They'll have their mirrors, the special home position for the mirrors to set out. And then they're going to have to use their various tools, protractors, templates, little rulers, so a metal ruler, or maybe even a bigger ruler here. But again, they're constrained to use all these tools inside this wooden box. You don't need the wooden box to practice at your schools, but you do want to make sure they've got that limitation. They realize they can't use a whole big giant tabletop. You're not going to get big giant meter sticks here, things of that nature that come into play. Then they need to be able to figure out with the beam coming in, again, this is the beam path marked by the line, that they can center this on there. But the other thing I strongly suggest is to make your giant protractors like this on like a transparency material. So they're transparent. So you can see to the table surface underneath. You'll be able to see where that line is, measure that angle, and it tells them, okay, I need to position my mirror on something like this. The rules do state that they can leave their templates and so forth in place. So I'd also suggest making lots of these things. Your tools could be a pair of scissors as well, right? The tools does not restrict what those tools can be, whatever tools they need to be able to figure out where do you place a mirror and where do you line it up. Because what you're going to have to do is figure out that here is the line that I want that mirror to be resting upon. To place that mirror perfectly centered right on that line so that it sets up right there. And then once they've got that angle figured out, now it's going to tell them, okay, my mirror is going to reflect the beam. Let me reverse it here. Where the mirror has to face the laser beam there. Then it might tell me, okay, so from that angle right there, knowing how it comes in, it's going to come out to this direction here. So what I might even suggest doing that would be even better is the law of reflection tells us that light reflects and comes off at the same angle to the normal. So what I would even suggest as a very good hint to do, go back here to our full screen view, is why not create a whole bunch of templates. I'll just draw on this one here, where each of your templates could have a base here for the mirror. So this is your mirror. And then create a whole series, because you don't want to do something odd. Why would you make angles at like 36 degrees or 47 degrees? Makes no sense, right? Most of your angles are going to be at like 45-degree angles. By 45, I mean if this is the normal to the mirror, you could pre-make some templates. And this is crude. Pre-make some templates. Get my scale back on there. Where you already have a mirror base and the actual line pass here, and make these angle lines very, very long lines. Okay? Why do they need to be very, very long lines? Let's go back over to the table and I'll show you, but these then are precise 45-degree angles. And maybe make some more templates like this at maybe 60 degrees or 30 degrees. That would give them a little bit more freedom to do things. But let's take our little template here now, those long lines to 45-degree angles. Let's go back over to our over there. That's my monitor, so I can see how well this shows up. I'll zoom in even on that a little bit. Because now I can place this whole template in here. And if I had scissors, I could cut that down. See how that's looking. Let me zoom in on that. There's my little template in there. What that allows me to do now then is I can place this mirror here. There's my mirror line up right there. There we go. So place my mirror right there. So there is the light coming in along this path, coming off at a 45-degree angle here. So it tells me where does my other mirror need to be. The mirror needs to be over here. As you can see on there, I can't quite get the steep angle down because mirrors won't support if I tilt it too much. But you can see on there how I've been able to easily and quickly, because again, only 45 minutes is all the time that we have. 4 minutes, all the time your students have to figure out how to set things up. So, okay, we're ready to test all this. Then the beam will come in here, go off at 45 degrees to strike this mirror here. If I had another small template version of this that I could set up over here, right? Then I would know how this beam is going to come off and go up in this direction to set a third mirror and set up and do it. Because again, this is extremely challenging. Or I could realize as well that rather than coming back over here, I could do one strike here, and then go over to our target point over here. So what the students should do, and this would be my strong recommendation, practice this at their schools at home, because if this blocking barrier right here is way up here close, which would be quite unrealistic, that would be a problem. If it was right here in the middle, we have a clear path around the barrier there. Back here, we have a clear path around the barrier there. So they really don't need to worry too much about where this barrier might be. They can have some pre-made templates set up, some idea of how are they going to position these mirrors and move it out. Because when they're given time in that 4 minutes to make calculations and so forth, this really isn't so much about calculations as recognizing the physical geometry of the setup of where these mirrors are placed. And I would strongly encourage them to practice because, again, of the time limit and the pressure, you do gain bonus points for using more mirrors, but at the loss of perhaps losing all those accuracy points. Because if you are so far away that you don't even hit the target, you're in great danger of losing all 25 of those accuracy points. You won't go negative, but you could lose all 25 of those accuracy points. Because generally, if you're that far off, the beam is not hitting all the mirrors. I've seen students try to say, well, let's lose all 5 mirrors. So you stick all these mirrors in here, trying to do all these different crazy angles. And that comes to find out is your mirror angles are off even just a small amount. So the beam goes here and hits this one, goes here and hits this one, but then it gets lost. So all you gain is points from 2 mirrors, and you would end up with 0 in accuracy because your beam goes so far off to be way off the scale and not measurable. So it's a highly complex process to align multiple mirrors unless you're extremely practiced in it. My recommendation is always use the fewest mirrors that you can comfortably continually set up with some success to ensure that the beam is hitting all the mirrors that you use, and the beam is at least somewhere over here near the target scale. Let me zoom back out here. Now back to my original setting. And I would doubt very much at regionals if anybody be successful enough to be able to strike a mirror sitting on the barrier as well. Because again, that barrier, the mirror there does not have to be perpendicular. The barrier could be tilted at the complexities. That is a case again where you could make a calculation of a new angle that shows up there. But you're much better off dealing with straightforward angles. So if you set all your mirrors so they'll always be at 45-degree angles, you can predict where that beam will end up and align itself more precisely. But this is the sort of thing that if teams have not practiced setting up something like this a significant number of hours at home, if they're thinking, oh, it's just reflecting light off mirrors, we can do that on the fly, I can guarantee they will have zero success. Because while it's very basics, it's a simple idea of just to reflect a straight beam off a flat mirror surface. Once you add even a second mirror, that alignment becomes extremely critical because, again, these are small devices. You need to line them to within like a degree of precision. And while they will have, I'm certain, some protractors to set in here, very difficult to maintain that precision across great distances to line up. As I showed you back over there on the board setting up, even a tiny, tiny shift in these mirrors, if the light travels from this mirror all the way across to the other side of the box over that long distance, a tiny shift in angle here translates to a huge shift in distance over here, and it's going to throw the beam way off the mark that sets up. All right, so we'll come back to our big display over here. Oh, there we are. And so I don't have anyone live here to ask questions. I'll just come back to emphasize again that the testing topics are a variety of concepts related to optics. The questions are broken out with several groups among the different topics. So you can provide reference sources and materials. You can find lots of that online in textbooks and so forth. Plenty of places for that. So you do want to be sure students have reviewed that. That is half the point scores for this particular event. Let them bring all the resources they can. But again, there is a limited time. While they only need 4 minutes for this performance aspect, there's time to get teams over there and back. So that means about 10 minutes of the period will be devoted to doing that device setup for the mirrors and the laser. And they'll typically have maybe 30 minutes or so to take the written exam, thinking about how the supervisor wants to set up for that particular location. So do bring the reference material, but generally there's not enough time to spend looking up answers. They need to be quite familiar with the material already. I recommend a simplified, broader, well-indexed list of references and sources that they bring with them, things that are not dense in reading, so that they can quickly look for the broader topic, help them maybe identify a key word or vocabulary word in a test question. If they're asking to do some simple calculations, they should practice some of those as well to be prepared for that. But that is the sort of thing that you as a coach kind of leave off to the students, particularly the C division. Middle school students will need more help with that. But for the other half of the event, which is that laser shoot setup aspect, I can't emphasize how little success teams in the past have had with that, no matter what their division, because they're just clearly not prepared and not well practiced. So you don't need, again, to build a box and all that fancy apparatus. Just get a laser pointer, mount it someplace above a table where they've got some space to work, and get them to practice how it interacts with these angles. And then again, build some of these templates, have those pre-built, have those ready to go, figure out how to make a template that fits in the box that they can interpret and understand how to use. Go so far as to say this is the one that works best, because students or teams may react differently. And I think if they create their own and see how the process works, they'll be more comfortable when they come to the actual tournament to actually participate in that particular event. But it's such a time crunch, already a pressure of them in terms of performance and competing overhand. So they do need to practice with protractors, with little rulers, whatever it takes them to line things up. There shouldn't really be that much calculation involved, a little bit, but it really is a simple process of the law of reflection, equal angles of incidence and reflection coming off that flat surface. But while you can do it with one mirror fairly simply, again, adding in simply one other mirror greatly it's a complexity there and how you're going to get things to line up precisely. And so practice, practice, practice as always. But in this particular case, the tools that they are allowed to bring are not limited. So have them be creative, and if you're uncertain if a tool is legal or not, check with the national organization, the back pages, or come back to one of us site directors, or we'll look up even information for you there as well. My understanding as I read the rules now is simply the word tools, and tools can apply all sorts of instruments like protractors and rulers, even a compass if you want to bring that in. but also the idea of using some templates. They also understand that those templates can stay in place while the actual laser is turned on to make the measurement. So these are things that could cause distortions, because once the students are happy with their setup, they want to be very careful and not disturb those mirror positions. But just the slightest disturbance can throw that beam path direction all the way off. All right, so I'm going to stop there with this presentation. So it's something that you can get to fairly quickly. Trying to highlight and emphasize the time there in the box itself, how you position those mirrors, perhaps use those templates. So wish you the best of luck with that and with your teams going on. There are pictures online. I'll end up with this one thing to show you here. Share my screen with my that page there. On, I will open it up properly. At this, let me go back here and I will share screen with it. This is the PDF of simply the laser shoot setup. Some of the box I've seen right there. It has, again, a bunch of covered mirrors and blocks and so forth in there. And you don't need to worry about, well, how do I get that thing constructed myself, or go into some sort of machine shop or wood shop or so forth to get it built. All you need is a laser pointer. And you can even just set it on top of a book or so forth to get it an inch or inch and a half up off the surface of the table. Set another little weight on there so it doesn't wiggle or move around. Have it shooting a beam that goes straight across. You can see in this drawing here, a little pencil line right along to that target point over there, straight on the other side of the box. And so you get, for this right here, you can just set up a piece of wood or the side of a cardboard box. Doesn't matter, very trivial setup to make. Then you need somehow to figure out there's a limited space between those two where the students can work, and then let them practice with it, seeing what the angles go forth. And again, you don't need high quality mirrors to do this sort of thing. Very simple, easy thing to do is to get some pretty compact mirrors or travel mirrors, something like that, fairly inexpensive, that you can mount to those blocks of wood. The key thing is for them to practice in this environment. And again, I would expect many hours of practice for the team that's going to be successful to figure this out, and have them start with just 2 mirrors. Make sure they can absolutely get 2 mirrors down, and they're pretty much almost 9 times out of 10 get those 2 mirrors to hit the target or reasonably close to the target. And then if they're feeling confident, they understand what's going on, maybe let them go to 3 mirrors. I would doubt very much at our regional and certainly the state level that any team would ever be successful in going beyond even 3 mirrors. As I mentioned before, the complexities, every angle has the potential for error. And you don't gain, again, anything if you're not hitting the mirror and if you lose a tremendous accuracy. So that's the balance. Get points for the mirrors, but also get lots of points for the accuracy as you set this up and try it out. All right, so I'll stop share there again in the video now, but wish you again the best of success in the future tournaments going forward. If this holds true to form, optics might be in for not only the 2024 year, but also perhaps the 2025 years. The better they can practice and perform now, the better they'll perform in the future. Good luck.